Hi guys, welcome back to Math with OG. In this video, we'll be looking at the set of real number system. Now, when we talk about real numbers, this has to do with deal with all the numbers you must have known right from your kindergarten. Think your kindergarten, the only numbers you knew were whole numbers, that's positive whole numbers. Think it's still basic 3 or basic 4 before you start learning things on negative whole numbers. Then also numbers that are not whole, that's your fraction as the case may be. Then secondary school you start hearing things like sod as the case may be. So all these numbers that you've learned so far in O level are called real numbers. Now if a number is not real, it means that the number will be imaginary. Now real numbers, imaginary come together to form what we call complex numbers, which is not what we are talking about now. When we are done with all the O-level topics in mathematics, when we are talking about A-level maths, we will look at complex numbers. Now these real numbers has several subsets under them. We have special type of numbers under real numbers. You can argue that you have your odd numbers, your even numbers, your prime numbers as the case may be, but we're not talking about those type of numbers. We're talking about a different type of numbers, which are your integers, your natural numbers, your rational numbers, and your irrational numbers. Now, how do we know that a number is an integer, a number is a natural number, a number is a rational number, or a number is an irrational number? That's what we'll be looking at now. And all these guys, they are all subsets of real numbers. Now, first one, set of integers, usually denoted by z. So when you are solving questions and you see something like this, a is a member of z, it means that a is an integer. So that's the meaning of this statement. So set of integers, this consists of all positive and negative whole numbers, including zero. So you have whole numbers, some are positive, some are negative. All these guys are integers, including zero. Zero is also an integer. So this guy, we can write it in roster form, and this is what you have, starting from very close to negative infinity, ending very close to positive infinity, minus 2, minus 1, 0, 1, 2. Now, you should have known by now, or if I have not mentioned it, that not all sets can be written in roster method. So we'll get to rational and irrational number, you see that it cannot be written in the roster method, just the root method. That means you can tell if an element is a member of the set, but you cannot represent it using roster method. Now the next is set of natural numbers. This consists of, okay, natural numbers is denoted by n. So whenever you see a is an element of n, it means a is a natural number. Please excuse me. Set of natural numbers, this consists of all positive integers. Now we just said integers are positive whole numbers, negative whole numbers, and zero. However, natural numbers are just positive integers. Sometimes we write it this way, z with a positive sign on top. These are positive integers and these are negative integers. So we denote it like this sometimes, while this guy means negative integers. So natural numbers are simply positive integers. Now we can represent this guy in roster form, which is n is equal to 1, 2, 3, 4 down to what? Infinity. So set of integers is infinite, set of natural numbers is infinite. And before we go into the rest, set of rational numbers is infinite, set of irrational numbers infinite, set of real numbers infinite, set of even numbers infinite, set of odd numbers infinite. I don't know about prime numbers. Now let's move on to set of rational numbers. What are rational numbers? This consists of any number that can be written in the form a over b, not just written in the form a over b. That does not mean if I write 1.285 over 1.7234 that this automatically is a rational number. No, this, okay, let me write it more boldly so I can see what I'm talking about. Let's say you have 1.285 over 1.724. This is also written in the form a over b, but it does not necessarily mean that this guy will be a rational number. Now they said if it can be expressed in this form a over b, not just expressed in the form a over b, but you see this numerator and this denominator, they have to be integers. So a has to be an integer and b has to be an integer. So if I can break this guy down to a form where the numerator will be an integer and the denominator will also be an integer, then we can say that this guy is a rational number. and I think it can work. Multiply by 1000, multiply by 1000, you'll be having 1285 over 1724. I don't know if anything can cancel out. I don't care if anything can cancel out. As long as this is an integer and this is an integer, this automatically becomes a rational number. You have something like this, root 2 over root 3. Can I express this guy in the form a over b? Not possible. So therefore, root 2 over root 3 cannot be a rational number because root 2 is not an integer. Also, root 3 is not an integer. Now, a over b must be in this form. A must be an integer, b must also be an integer, and b must not be equal to 0. So I can't have 17 over 0 because whenever you divide by 0, it tends towards infinity, and infinity is not a real number. So b must not be equal to 0 because putting this guy at 0 will make this guy to be undefined. That's another way you can put it. Also, you should note that whenever any number exists in this form a over b, where a is an integer, b is an integer, these guys will always form either a terminating decimal or a recurring decimal. So these should not be integers. This is rational numbers. Rational numbers, rational numbers always forms either a terminating decimal or a recurring decimal. It means whenever I have a over b, you will always get a terminating or a recurring decimal. What are terminating decimals? What are recurring decimals? Now let's play with this mathematics. 2 over 5. 2 over 5 should give us 0.4 terminated. So that's a terminating decimal. Now let's try another one. Let's say 10 over 3. 3 into 10 is 3. Remember, 1 into 10 again, you have 3, 3, 3, 3. Now if we keep dividing, we'll be getting 3, 3, 3, 3, as the case may be. So this guy is a recurring decimal. So I put a bar here to tell that 3 will keep on repeating itself. This guy is a terminating decimal. A recurring decimal can also exist in this form: 0.272727. So you have, I can now put a bar here to tell that the next will be 272727. A recurring decimal can also appear in this form: 4.285 So this is also a recurring decimal. There's a way in which you can change your recurring decimal back to its form in a over b. I guess we'll be looking at that in future classes. So because it's not that important, I'll say change this guy to his form in a over b. So there's a way you can do that. So we'll be looking at that some other time if I remember to talk about that. So this is what we have for terminating decimal, this is what we have for recurring decimal. So any number that exists in this form will either exist as a terminating decimal or a recurring decimal. Now you should note that the fact that you are given a number and it's not existing in this form does not mean you cannot make it exist in that form. So any number that can exist in this form is a rational number. Let's say you are given this number, a positive number 7. You are asked, is 7 a rational number? You might be forced to say no, it's not a rational number because this is just 7. But you are wrong because 7 can exist as 7 over 1. This is an integer. This is an integer. So since 7 can exist as 7 over 1, this guy automatically becomes a rational number. So I can say that all integers are rational numbers, including 0. 0 as a number can be equal to 0 over 1. 0 is an integer, 1 is an integer, so this is a rational number. Remember, you are told that the denominator cannot be 0. That does not mean that the numerator cannot be 0. So this is a rational number. So all whole numbers are rational numbers, be it negative whole number, positive whole number, or 0. They are all rational numbers. Now you will now ask yourself that, okay, we know that it can exist in this form 7 over 1. Now, how can this guy form a terminating decimal or a recurring decimal? Very easy. 7 over 1 or 7 is the same thing as 7.0. This is a terminating decimal. It terminated 7.0. So you can see that all whole numbers are rational numbers. Now the last one, if all numbers are rational numbers, it means that all integers and natural numbers are rational numbers because integers are whole numbers and natural numbers are also whole numbers. Now, irrational numbers, okay, before we look at irrational numbers, if I were to write this in its rule method, rational numbers is equal to a over b, such that a and b are integers and b cannot be equal to 0. Also, a over b is a terminating or recurring decimal. So that's how you write this using the rule method. You cannot represent this in rational method. It's not possible, because the rational numbers, they are scattered. They are not sequent, or they don't follow each other sequentially. So you cannot write this using the roster method. Now, a set of irrational numbers, the opposite. A number that cannot exist in this form, a over b, where where a is an integer, b is an integer, and b cannot be equal to 0. So a will be an integer, b will be an integer, and b will not be equal to 0. An irrational number can never exist in this form. So examples, you have your pi. Your pi, you punch it on your calculator, is equal to 3.142, so many values, to the extent in which your calculator can calculate its decimal point. So when you get an advanced calculator, some can calculate up to 20 decimal, 30 decimal, 40 decimal, but your pi does not terminate. And your pi is not equal to 22/7. Your pi is approximately equal to 22/7. But if you punch your pi on your calculator, the answer you will get is different from punching 22/7 on your calculator. So your pi approximate value is 22/7, but its real value is 3.142 with so many values. Then you have your E is another constant. I think it's called Euler's constant. It's also in your calculator, which some of you mistake for exponential. Euler's constant that you see in log with e, which is the same thing as what your ln, or e raised to the power of x. So this is a constant too, is an irrational number. It is 2.7182 with so many values that will never terminate. Now, anything you call surds are irrational. Surds are irrational root of a number. So any number that you cannot find the perfect root is a surd. So for example, you have your root 2. Root 2 is a surd. If you point to your calculator, to give you a decimal that does not terminate. You have your root 3, you have your cube root of 2, cube root of 3, fifth root of 5, fifth root of 2, seventh root of 9. All these are irrational number or surds. Now, real numbers. Real numbers is a universal set. So real numbers consist of all rational and irrational numbers. As easy as that. Real numbers consist of all rational and irrational number. So now you can see that rational numbers and irrational numbers, they are subset of real numbers. However, let's start from natural numbers and integers. Integers are positive, negative whole numbers with 0, while your natural numbers are just positive whole numbers. So I can say my natural number is a subset of integers, because everything you can find in natural numbers, you find them in integers. Also, these integers, they are subsets of rational numbers, because all whole numbers are rational numbers. Now, this rational number, as you can see, is a subset of real numbers. So your natural number is a subset of integers. Integers is a subset of rational numbers. Rational numbers is a subset of real numbers. And lastly, your irrational number is also a subset of real numbers. Your irrational number is also a subset of real numbers. We've not done the complement of a set. I would have added one last thing, where I would say irrational numbers is the complement of, your rational number is the complement of irrational number, and also irrational number is the complement of rational number. So when we get to complement of sets, you understand that better. So that's that for the set of real number system. Now, next video, I think we'll just introduce the meaning of Venn diagram. Then after that, we'll move on to operations in sets, and we'll be doing that simultaneously with Venn diagram representation, rule method representation of these operations. Thanks for watching this video. Kindly use the like button, use the subscribe button, use the share button, and don't forget that if there's any error in what we solved or what I talked about, you can leave that in the comment section. And if you have any question, you can also use the comment section. So thanks for watching once more. See you guys in my next video.